Gerard Watts. So I learned a great deal from his old papers on defects interfaces. So I think it's very timely to that Gerard starts this.
Okay, well, thanks very much to the organisers for inviting me to give this talk. Already, Frank said I've been in this a long time. Indeed, my first paper on boundaries, I think, was 96, and on defects, a bit late to come into defects in 2004. Today's talk is on something which has been around an awful long time, but there are some nice things about them. They are defects in two dimensions, which are not necessarily topological. So a lot of the talks here have been about topological defects. But these don't have to be topological. All we require is translation invariance. And in that class, there are many interesting classes of defects, many interesting questions you can answer. I'll go through a couple of them today. I should thank my co-authors. It's based on one collaboration with my ex-student Max, student Faisal, and two young Indian postdocs. And a second collaboration with Federico Ambrosino, Ingo, and work in progress with Natalie down at the front here. So there's two streams to this, but they both fall under this title here. Very quick plan. I'm going to say what I mean. I don't assume everybody knows what I mean. Some properties of these translation invariant defects, and these are the two streams on two threads. One is generalized Gibbs ensembles, which I'll try to explain, and the other ones are perturbations of topological defects. So here's the standard picture. Sorry, Frank, I should ask you, what time am I meant to finish talking?
About the whole talk lasts 1 hour, including questions.
So this, but just the end time. I'm looking at the clock up here.
Yes. Okay. 10:30.
Okay, fine. So I'm always working in two dimensions. I try occasionally to get into three and some or four, but it's very difficult. I end up being stuck in two. And in two dimensions, boundaries, defects, interfaces are often thought of as very much the same thing. So here's a bit of two-dimensional space with some boundary, with some defect or interface in here between two theories. I've called them C because I keep thinking about conformal theories. But we're not only thinking about conformal theories here. I've called them C by sort of force of habit. And the folding trick means I can just take this interface or defect here, fold the system over. It may not be exactly the same theory, but it's obviously clearly related to it. And then the interface or defect here becomes a boundary condition on C1 opposite times C2. So in almost all situations, you simply think, well, I can look at one. Whatever situation is easier for me to think about them in, I'll think about them in that context. But the translation invariance is something which is inherently a property of defects. Of course, you can express it as a condition on this boundary condition, but it really is about, I take this defect here and I simply move it sideways. That, of course, breaks this picture, because this thing is fixed. That's a fixed point of the folding. But here, I move it sideways, and the translation invariance says I put some, whatever, local insertions, whatever you like in there, move the defect sideways, and you get exactly the same answers for whatever you're calculating. That's all I mean by translation invariance. It's not translation invariance along the defect. I would call that homogeneity or something. It's translation perpendicular to the defect.
Excuse me.
Yes.
So this has to be some space where the translation makes sense?
Yes, indeed.
So it's a rigid translation?
It's a rigid translation, indeed. So we either think of it being the plane or a cylinder where the rigid translation makes sense. In particular, I'm thinking that this thing has a definite extent. So it could be infinite or it could be finite, but that's going to stay the same. So, yes, it's a limitation, indeed.
You could have a Riemannian manifold and then move along the normal direction. So
manifolds are always flat, I'm afraid. So the simple property that, sorry, wrong button. These are simply reflectionless. If I imagine here's my defect and I send something in, charge, energy, doesn't matter what, it can sort of hang around the defect for a bit and be reflected back. So if I emit it here and absorb it here, that's a perfectly plausible procedure. But because this defect metric translation invariant, if I move it sideways, I can move it so far out of the way that these 2 points are no longer causally connected. So it's impossible in this context for there to be reflection from a translation invariant defect. So we could have called them reflectionless, except that that might be a wider class. And just say this is not necessarily the same as purely transmitting, simply because we know that defects in a massive theory, so they say it doesn't have to be conformal. Think of a massive theory, this could be massive particles. Defects can have bound states. So I mean they can have states associated to them of finite energy localized on the defect, and that can be less than the mass of a particle. So it's possible for some particle, for example, to come in, leave some amount of energy on the defect, carry on through, but this amount of energy, if it's less than the mass of a particle in a massive theory, can't be emitted, because there's nothing in the continuum spectrum it can be in the bulk it can be emitted into. So theoretically, it's possible for there to be reflection, we said there isn't any, transmission, and absorption. It seems likely that this doesn't happen for CFTs. Because the bulk spectrum is gapless, you can emit any amount of energy into the bulk. But there's no argument that anybody so far I've spoken to has come up with or says they know that they can prove this for CFTs. That's why I wanted to call them purely transmitting, and then I realized they're not. They're actually reflectionless. And in the case of massive theories, it's quite possible that they're not the same thing.
So you're postulating that the bulk is gapless?
No, I'm not.
Okay, but you just said the bulk is gapless.
If the bulk is gapless.
If the bulk,
If. So no, we will see, we treat both classes of theories, both massive ones with a gap and massless ones with no gap.
Can you back to the previous slide? I don't understand the first picture on this slide. What does it mean this? It is reflected on the...
No, that's what reflection would be.
Ah,
okay.
Reflection less,
but because I can move the defect, you know, in a sorry, Minkowski, where's my pointer gone? There it is, it's tiny, sorry. This is meant to be a Minkowskian theory, so things should travel no faster than the speed of light. This is looking like it's going at the speed of light, but still. It's possible to have a reflection like that. It doesn't mean it has to be reflected straight back. You know, if there's a repulsion or an attraction, either way, it will retard the reflection of the particle. That's, you know, known in classical physics very obviously. So this is what reflection could look like, except because our argument is that it shouldn't depend on where the defect is. It says it can't happen. Okay, so yeah, maybe next time I'll put a big red cross through this. But the nice thing is that these emit a fusion product. Because the thing is translation invariant, there's no distance dependence between the defects. So you can just bring them together, and you get a nice or not so nice fusion product, which may or may not have properties that you're used to. But still, it is a fusion product, and you can think about its properties. So that's one of the nice things that is retained by these translation invariant defects. So we're very familiar with topological defects. We're also very familiar with conformal defects. A lot of the talks here have been about conformal defects of some kind or other. And it's relatively straightforward to show in generality that translation invariant conformal defects are topological. I should thank Chris for pointing me at the proof. It's true in general. You can look at properties of the displacement operator in correlation functions with local insertions, and you can see that it has to vanish in general. But there's a very simple algebraic argument in two-dimensional CFT. So I'm going to take a cylinder. That's my space. Here's my defect. I think of it acting. So it's a Hilbert space associated. This time is going in this direction. It's an operator. In this formulation, the defect is an operator. Translation invariance means it commutes with generated translations along the defect, which is that. Conformal invariance is this property. So those are well-known statements of translation invariance and conformal invariance, and you combine them and you look at the commutator of this with this, and you instantly see that it commutes with all generators. Sorry about that cough. Let me just. So if it is translation and conformal invariant, it is topological. So what this means, in fact, generic translation invariant defects are not scale invariant. Generic ones are not going to be conformal invariant, not even going to be scale invariant. So there's an action of scale transformations or the renormalization group flow on defects, and it's believed, not proven, it's a physics argument, it's believed that in the large distance or infrared limit, you end up at a conformal field theory. So in the infrared limit, your translation invariant defects will become conformal. And since they remain translation invariant, they're going to become topological. So if you look at a renormalization group flow, translation invariant defects flow to topological defects. That's a very nice property they have. And I'll come to that later in the talk. So, any questions on the setup before I move on to a couple of examples? Okay, so these are the two things I've been working on for the last few years, and they both fall into this class of things. One of them is things called generalized Gibbs ensembles, which I'll explain. And the second one are chiral perturbations of topological defects. I put chiral here. I should probably not put chiral there. I should probably put perturbations of topological defects.
I'm sorry, could I ask a really ignorant question? I'm just a mathematician, so I don't understand a lot of these things. But when you look at the renormalization group flow, so you're changing the theory, but does it somehow preserve the translation invariance of the defect you put in, or what's going on there? Or does the defect flow with the renormalization group? How should that be?
So that's a good question, because it's possible there are defects that I haven't imagined which lose the translation invariance property.
Under the flow.
Yeah, I think so. It's a good question. I thought about it when I said this and suddenly realized I haven't thought about this. The ones we talk about keep that property of translation invariance. But indeed, it's a question that we will have to think about. So these are the two things I've been looking at, which, as I said, fall into this class, and I thought I'd crush them together in the talk because I've got an hour to fill. The first one, generalized Gibbs ensembles. So this is not something I wanted to study, it's something I started thinking about soon into my PhD, which was to understand something characters, like regular characters of representations of two-dimensional objects called W algebras. So hopefully you've heard of the Virasoro algebra. It generates conformal transformations in 2 dimensions. It has generators Lm, and you can take a character, which is a trace over a representation of Q to the L0, it counts the number of eigenstates of a particular eigenvalue of L0. So that's a character for a representation of the Virasoro algebra. And it's well known that these have nice modular properties. So this Q here, think of it as a complex number, but if you write it as e to the 2 pi I tau, that then relates this to a property of a torus. And that torus, and the CFT only understands the complex structure of the torus, so, or the conformal structure. So if I do a transformation that keeps the complex structure the same, what will happen is that these have to recombine into a linear combination. So this is a property of traces over representations of generators of conformal transformations. In the nicest case, this is a finite sum. In more complicated cases, it could be integral. You might even argue whether I quite know what I'm doing. But still, this is a fairly standard property of a large class of representations. This W algebra adds a set of generators. So M here is an integer. I've added an extra set of generators. It's like going from SU2 to SU3. I add some extra things. I've got some commutation relations between these. I'm not going to display those because they're too complicated for you. They're not linear, but they make sense. And so since these commute, I might want to think of them as like a Cartan subalgebra. They could be simultaneously diagonalized. And the question is, let's think not only about counting the eigenvalues of L0, but the simultaneous eigenvalues of L0 and W0. So that seems like this is a well-formed object for representations of I'm looking at, large classes. If Q has modulus less than 1, this is almost certainly going to be convergent. So here's a function, depending on representation. Does it have nice properties in particular under this map? Tau goes to -1 over tau. So I started thinking about this in my PhD, and I couldn't do it. And I was asked again to think about it about, I don't know, 10 to 15 years ago, because these came up again in ADS, CFT, or counting states of black holes, and the same question came up, and I still couldn't do it then. But thanks to this collaboration with Max Faisal and these 2 young Indian postdocs, we have come up with an answer. Sorry, let me get rid of that. So we have an expression for this asymptotic expansion. Okay, W0 is unbounded. This is not going to converge for typical real alpha. It's going to converge for purely imaginary alpha, but it's not going to converge for real alpha. So I'm not going to expect to have an expansion in alpha that's convergent. So this is an expression here for the asymptotic expansion. So I've changed Q to Q hat. I was on the modular transformation. And Q hat itself takes a form as a sum. So here's some factor. It's got alpha, powers of alpha. It's got the parameter tau, some other bits. And this is the 0 mode of a field on the cylinder. So this little hat here means you've got to do a map from the cylinder to the plane, which makes it vastly more complicated as an expression, but as a concept it's very straightforward. And this is recursively defined. So I start off with, I didn't write it down, did I? No. W1 is just W. That's the field you start with in the algebra. Then look at what's W2. Well, I take a sum. This sum here is actually just W and W. This 2 here means take the second order pole in the operator process expansion of these 2 things.
Commutator usually is the first order pole, and here it's nothing to do with the commutator.
No, we're taking the 0 mode, and the 0 mode of the first order pole always vanishes. Good point. So this is the second order pole. So this is very nice. It's related to things called otter trees. So these are trees in the plane where you have to remember where things are on the plane. Normally you talk to a graph theorist about a tree. They don't really mind if you just swing it around. You've got things hanging down and you move them around, and if you do a flip, it's the same tree. But these, you have to count them separately. And we can't even, you know how many trees there are where you don't care of the order. You know how many trees there are where you do care of the order. We can't count yet the number of equivalent trees. So it's a little upsetting we don't know some things about this, but this is a perfectly good formula. It's a recursive formula. Tells you what these are. You put it in here. We sent it to the referee. They asked us very sensible questions. Do you know if this converges? No, we expect it doesn't converge. We expect this in asymptotic expansion. Are you guaranteed that this sum will itself then be a local field? No, you're not guaranteed it will be a local field. You're doing infinite sum of fields. You know, if you take infinite sum of derivatives of fields with the right coefficients, that's what's a field somewhere else. It's a Taylor expansion. So there's not necessarily a local field at the point you first thought about. But in the context of this formula, it works perfectly well. So it gives you, expanding out to any order in alpha, it tells you exactly the modular properties of these quantities.
So what is small, what is large? You know, your alpha and tau. What is this? You say it's an asymptotic expansion.
So yeah, because this will not converge as a series in alpha. Neither side. This one we know doesn't. This one doesn't either. So it's really a generating function for endpoint functions for insertions of W0 to the n. So this is a formula for the modular properties of the traces of W0 to the n.
For approximate the answer, what is small, what is large? So
Alpha doesn't matter. It's just alpha is just just a placeholder. So alpha doesn't matter. And let's have mod q less than 1.
and tau goes to 0.
Tau is, well, somewhere in the upper half plane, like normal, but. So tau just parameterizes your torus. We want q to be modulus less than 1. And because this is a formula really for coefficients of alpha to the n, we don't care what alpha is. If you want a function, this function is probably going to converge for alpha purely imaginary. You'll be able to define a function. But that's not what we're doing here, except when we can define it for all alpha. So there are some cases when you can. This is typically a very hard problem, as far as we can see, because the eigenvalues that is W0 are just a mess. I mean, they're roots of algebraic equations of quite high order. We haven't got a particular handle on them. But at particular values of the central charge, so conformal field theory has a central charge, it's a property. And at particular values, you can do it. So at c equals -2, one of the favorite unpleasant values of c, you can write a formula down. So I haven't told you what the trace is over. It's a trace over a symplectic fermion space. That's why there are products of 1 plus something. That's because you're counting whether there is a fermion mode or not a fermion mode in your state. And k is the eigenvalue of L0. K cubed is, typo, k squared. K squared is the eigenvalue here of W0. And there's a plus and a minus because you've got two sorts of fermions and they have opposite charge. So this is an expression for this trace, modulo the typo. And that's the exact answer for its modular transform. There's an integral bit, that's to do with the ground state energy, as a product over n of 6 terms. It's also, there should be a plus minus here. It's over n and over plus minus. So each of these corresponds to two things. So there's 6 factors here. One of them comes from the asymptotic expansion. Because it depends on this function z here. And only the first one is perturbative in alpha. These two are not. So something fundamentally different is, you turn on alpha and suddenly these come into play. They're not there in any sense perturbatively. So it's rather nice. This is sorry. Look at the next slide. It's rather nice. You can actually prove this. So we came up with it in a simpler context in the first paper with Max Downing, numerically. So we looked numerically at this function up to very high order, 20,000 terms or something, trying to work out what we had to add to this bit here that we knew about to make it, first of all, the function should be real, in our case, and then it should be actually the right number. So we came up with the analogues of these 2 extra terms numerically. We were really pleased, because the first paper we just conjectured just this bit, and then the second bit we thought, oh, to prove this, you can prove it by relation to thermodynamic beta ansatz. And then Max went away to a number theory and physics meeting and met Don Zagier and had a big chat with him and found that Don had proved a simpler version of our formula about 2 months before we published it. So we were really pleased. We'd found a formula that Don Zagier thought worth publishing. Okay, so he's a big name in modular forms and number theory, and so we were really pleased. Didn't matter that he proved it, that's fine. And he also found it numerically. That was also an interesting thing, is that he's a pure mathematician, but in order to come up with what his conjecture should be, he looked at this numerically, also to very high order to find out what it should be, and then he believed he could prove it. And we were just happy to have found it. Okay, but then Max went away and proved it. So there's a rigorous proof of these formulae. What's interesting is that exactly the same thing comes up. These terms here are residues. Residues when you pass a contour through an integral, a contour in an integral through some singularities, and that's what you do in physics when you're looking at thermodynamic beta ansatz to get excited states. Excited states correspond to poles in your integrand, and you pass it through the poles and pick up extra terms for each excited state. It's normally complicated, except for these free fields, it's relatively straightforward. So that's how we justified our formula from TBA expressions for ground state energies continued to get excited state energies. An old story about analytic continuation of the spectrum. The spectrum here is connected in the complex plane, and you can continue from one to the other by continuation, which is equivalent to changing contours of integration. In the pure maths proof, what you do is you do Poisson summation. So you take the logarithm, it's a sum, you have to do something to make it symmetric, which is differentiated. You've then got a sum over the integers, which you can Poisson sum, and that gives you an integral. And it's calculating this integral, and it picks up exactly the same terms in exactly the same way by these terms crossing the contour. So this looks very, very strange to be a pure maths expression, counting the number of singularities in an expression in the upper half plane, but actually it arises exactly the same way. So it's a really nice way that the same techniques and the same methods in 2 different contexts give the same answer.
Oh, excuse me.
Yes.
So Zagier was also trying to compute this trace, or that's some other expression?
No, he was looking at the case where he just had k cubed. That's why I wrote cubed.
Oh,
Okay? This should be squared here. In this model, it's squared. But he had just one product of these. Without this term, he was looking at 1 plus q to the k cubed, I think.
Okay.
So this counts the number of partitions of integers into cubes. So that's a perfectly reasonable mathematical question. How many partitions are there of 17 into cubes? This tells you the answer. And if you want to look at the large asymptotics, the way to do that is to look at its modular transform. So if you want to look at asymptotic distribution of these numbers, that's why you do it. So you know, it's a perfectly good combinatoric question, if you like, with sort of quasi-modular properties. So I should say, you should go to the library. It's fantastic, because you get to see things nobody else gets to see. And they'll bring out sheets of Ramanujan's lost notebook for you to look at. And Zagier published his result in a paper dedicated to Ramanujan's root memory. So go to the library. So the relation to defects is that this expression here, actually, you can think of as counting the states in a theory where you've put a defect in your theory and the fermions pick up a phase when they pass through it. It's a purely transmitting defect for the fermions behind this construction. And again, this should be squared. Alternatively, I could replace this by something else. Something else has the cubed property. Doesn't matter, it's a different field. So there's a direct relation. This what looks like a straightforward trace here of an operator ends up actually being related to a defect. And it's purely transmitting. The fermions go straight through. Each of them pick up a phase. And that will give you this partition function. These come from the quantization conditions on the fermion modes. You think of, if I think of this phase here, what's it mean? I get a cubic equation for the energy momentum relation, and these are the solutions for the energy. And so we've changed the Hilbert space fundamentally. The Hilbert space of our theory with a defect is different from the Hilbert space without a defect. So there's no way we should expect to be able to get a perturbative expression in this context in terms of the original Hilbert space. So we have to change it fundamentally into a defect which is purely transmitting and translation invariant. So that was the motivation. But then you see what we've done actually is we've simply taken our original Hamiltonian and added in a bunch of conserved quantities. So take the energy, add in some conserved quantities, so you change the energy, and that's what physicists will call a generalized Gibbs ensemble. So a Gibbs ensemble is when you want to look at the proper thermal properties of something. You take the sum of 1 over kT minus 1 over kT times the energy. That's the Gibbs ensemble. It tells you what's the probability of finding a state with a certain energy. It depends on the temperature in this way. If you have other conserved quantities, like momentum, you can add that in. But you can have higher ones. In an integrable theory, you can have conserved quantities of arbitrary high spin. So you can add them in and wonder what's the distribution. So that's a generalized Gibbs distribution. It generalizes a distribution when you just have temperature and energy to one where you have more conserved quantities and more chemical potentials. These alphas are called chemical potentials in the physics language. And what we can see is this is going to be actually a translation invariant defect. You can see its translation invariant if I think of inserting this in this picture. Because it commutes with H0, I haven't had to say where I've inserted it. This is a trace along a cylinder, but I can put it anywhere because it commutes with H. So from this point of view, if I think of it as inserted at a point, I don't know where that point is. And in the opposite picture, I should think of it as a defect inserted somewhere. So here, this is a fixed time slice. It's inserted at some point. It can be anywhere.
Sorry, is this just, I think, previous slice? That formula, I think, can be represented as an horizontal, so not this It's just a phase. You do the sum in the trace for each state. You just do the center transformation. You put the chemical potential as an alpha.
So I'm
I
confused.
think the picture is not the straight line, but the horizontal circle.
No, that's the first picture. The first picture is the horizontal circle. Okay? That's the first picture, is the horizontal circle. And the second picture is the vertical. I'm happy to discuss it. Maybe we've missed something, okay? I think that this is expressing in two different ways. One of them as the horizontal circle, picking up one for each state. Again, so
Is the horizontal circle, then by definition is the translation moment.
there's translation invariant this way. So the circle, we're talking about the circle being this way, and it has to be translation invariant that way. It's always possible we've completely missed something. But let's talk about it afterwards. Sorry, time's pressing on, my cough's not getting better. So I talked about it for a CFT, but we can also consider the massive case. And this, at least for us, this is much less well developed. We wrote a paper with Samir Murti, who knows about Jacobi forms and things that occur in massive fermionic theories. And we started thinking about this in the massive case, but we haven't pushed it very far. This is not a property of CFTs. Modular invariant is a property of any theory you put on a torus. You put a theory on a torus, Euclidean theory, and then turn the torus round, it's still the same theory, and things you calculate still have to be the same. So exactly the same, we looked at one-point functions only of conserved charges in a massive theory and looked at their modular transforms. And they're well behaved. And so we believe everything else will go through in a much more complicated fashion involving much fancier modular theory. But there's nothing in principle we see that's going to stop this to happen. So that's as we believe our asymptotic expression we wrote down. I wrote it down for the W3 mode W0. There's nothing special about that. That was the first one we looked at. For some technical reasons, and for our checks using Mathematica, this was the simplest case to look at. So we checked our formulae. First of all, we checked them extensively algebraically. And we're in the process of proving them. But there's nothing special about that. Secondly, if we go back and look at this, this is the first charge in a hierarchy of charges, called the Boussinesq hierarchy, which is going to reoccur in the second half of the talk. And we were misled. In the very simplest cases, this Q is a sum over charges in the same hierarchy, in the very simplest case we looked at. But that's not true in general. This formula, some analogous, some adaptation of this formula, replace the powers and the numbers and so forth, is going to work in general for anything you put here, any zero mode you put here, will give you an expression in terms of zero modes. And there's no particular fact that they are a commuting hierarchy. That was a complete red herring from our first paper. So we think this formula is just working in general. And it's a generalization of a result that Dijkgraaf had way back in the late 80s, early 90s, for zero modes of chiral currents, except there's a technical condition in his that these don't satisfy. So these are the generic case, and he looked at a particular case. We can't adapt, as far as we can tell, we can't adapt his proof. But this will result to his in the case when these satisfy some further technical condition on a pre-Lie algebra structure, which you don't need to know about. So that's the first thing. These modular transforms of what look like generalized Gibbs ensembles are in fact translation invariant defects. And in this case, the ones we found are purely transmitting. And these are relevant for charges of black holes in 3 dimensions, for entropy formulas. They have physics applications as well as just being a nice maths answer to what is the modular transform of this character. They actually have applications. So hopefully we are going to go back to that once we've proven our formula. Although we may not be the best people to do it. Go on.
Can you just say that these defects are always like trivial defect perturbed by these high spin charges? Well, the densities, some irrelevant operators. Do they always look like that?
We couldn't make that work because they're irrelevant. There are singularities. There are divergences. We couldn't come up with any sensible expression for this modular transform defect as a. I think my cough's putting Frank off. as a perturbed defect. No, we tried, but we couldn't. We had expressions that made no sense. Formal expressions that really made much less sense than even I was happy with, even as formal expressions.
So in some sense, these defects are very kind of non-perturbative.
Yes. So the second example is perturbations of topological defects. So here are topological defects. So I've drawn it wiggly because you can move them around. And I'm talking in a conformal field theory. I have Z and Z bar dependence in the Euclidean theory, and I can have chiral fields on a defect. Normally chiral fields are quite unpleasant in the bulk. You don't want to have them, or you want them to be defects terminating operators or something. But here, actually on a defect, there's no problem. Oh, thank you very much. It's very better than the coffee. But we don't want topologons, we want straight ones. So we're going to take our defects to be straight, and we're going to perturb them. We can deliver perturbing them by a sum of operators. So what you do, what this means is, in a correlation function, I've got some brackets here for a correlation function, I just insert this quantity, and that is what my perturbed defect is. I put the defect in, I put this exponential in, that's a perturbed defect. That's what I mean. Why did we get into these? So this is not new. These have been looked at for ages and ages and ages. So I think I'm going to mention 94 as one of the first papers for the things we do. But why do we come back to them? We came back to them because end of last year and this year, people started conjecturing, are there new RG flows? So this means, this is notation, sorry, I've got a slide later. So this means a conformal field theory, a particular conformal field theory. This is a particular field. So I perturb a conformal field theory by a field. And it can happen that the RG flow takes you, it will take you to a conformal field theory. That's what RG flows do. They end on conformal fields. We can end on this interesting non-trivial one. People conjectured these by consistency conditions with non-invertible symmetries. You say, are there a bunch of non-invertible symmetries which are preserved along this flow? You get certain matching conditions between the two endpoints. And there were a whole bunch of plausibly or potential flows conjectured that commute with a set of non-invertible symmetries. No one knows whether non-invertible symmetries in this way mean your theory is going to be in any sense integrable. They can constrain the flow. They might tell you something about the fields you need to perturb by, but doesn't obviously say it's integrable. So what was interesting was that in this particular one, this is one of the simplest of these new ones, there was a thermodynamic Bethe-Ansatz equation conjectured for the ground state energy, which passes a lot of plausibility tests by Federico Ambrosino and Stefano Negro. They came up with this. They said, well, and it's sort of a mystery why it works. They throw some regular ingredients in, they get an integral, and not only does it give you the right change in central charge, that's the property that defines the CFT, it also has an expansion in powers of the correct things that correspond to infrared and ultraviolet expansions of the perturbation. So they pick up the correct dimensions. It's very strange. So the question is, are there any other indications of integrability of this flow? So here are some simple, known to be integrable flows. This is this is the tricritical easing model going to the easing model. This is known to be consistent with the preservation of non-invertible symmetry. It's very well described in many ways. It's massless. It goes from a conformal field theory to conformal field theory. This is one that doesn't go to conformal field theory. It is something called Li-Yang. This is a non-unitary conformal field theory. It has only one relevant perturbation, and it goes to a massive theory. So these are well-studied. You know, if you're going to study integrability of RG flows, these are some of the very simplest ones you're going to use as your toy models. And so here are some measures of integrability. Is there a thermodynamic beta-Ansatz system, a bunch of coupled nonlinear integral equations for the ground state energy along the flow? That's what TBAs are. Coupled nonlinear integral equations, typically very fastly convergent, if you iterate them, which will give you numerical values and expansions in the ultraviolet and the infrared for the ground state energy of the system. So definitely yes. For tricritical easing goes to easing, definitely yes for the Li-Yang model. These are known to have local conserved quantities. So that means the integral of a local field, which means a conserved current. So in physics terms, a conserved current, d mu, j mu is 0. This gives you a conserved charge. So there are conserved charges which are preserved along these flows. Sorry, no, not preserved, which commute with the Hamiltonian at each point. For this tricritical goes to easing, they have spins 1, 3, 5, 7, and so on. For scaling Li-Yang, they're 1, 5, 7, 11, and so on. And if you think about them, these are the exponents of affine SU2. These exponents of, well, I've written it down here, that should be A22, another typo. So twisted SU3, affine. And they're related to classical integrable models. This one's related to Sine-Gordon. This one is, who is that? Shabat Mikhailov Shabat, I think. Bullard, Dodd, and Tsitseka. So various names associated to a classical integrable system which has these conserved quantities and which can be related, and this can be thought of as a quantization of that system. So these are integrable, related back to classical integrable models. And here's our new one down here. Well, there is a TBA system, but it's not been derived from anything. TBA systems normally are derived from integrable S matrices. We don't have one of those. So there's no S matrix for a derivation. There's just an integral equation which gives plausible answers. We looked for local conserved quantities. So this is a quick summary of the method from Samologikov from 1989. This is not the counting argument. There's a counting argument that proves the existence of charges in some cases. This is another one based on perturbation theory. Don't need to know the details, but we checked up to weight 20 in the conserved current, and there is no local conserved current in this model up to weight 20. So one of these measures, one of these related things here, these local conserved quantities, doesn't exist, as far as we can tell in this model. Further conserved quantities, there are these translation invariant perturbed defects, which are well known, for example, in Li-Yang. These are the foundation of the Bazhanov-Lukyanov-Samologikov free field construction that gives very many properties of perturbed systems. They do it in terms of a free field construction, come up with large numbers of very impressive results. I think in many cases the proofs are missing somewhere in a filing cabinet. I don't know where they are. Ingo did an intrinsic CFT construction, which you can prove works, but is somehow many years after this thing. And the starting points are topological defects. So I said in the tricritical easing model, this flow preserves a non-invertible symmetry. That's not what we're talking about here. We're instead not looking at topological defects that are preserved along the flow, but instead ones where the topological symmetry is broken, but the perturbed defects survive. So, technically, we consider the bulk as a perturbed CFT. So you imagine the action is a CFT action perturbed by the integral of some local field. It will be a scalar field. H and H bar are conformal dimensions of the field, integrated over the plane. There's a coupling constant mu and a 2i in there that makes some of the i's go away later on. And we want to think about a perturbed topological defect in S0. So S0 is a CFT. It has some topological defects. When we think about perturbing it in the way I said, we'll call it d of lambda and lambda twiddle, and we take two fields, we hope they exist, of the same left and right dimensions, but this is chiral with H, and that's anti-chiral with H bar, which is also H. So that's a perturbed defect. We ask, what are its properties? In particular, to be translation invariant, does it commute with a Hamiltonian? So can we move this up and down the cylinder and not change any physical quantities so long as this defect doesn't pass through a field insertion? So there's an expression for the Hamiltonian. There's a recognizable conformal Hamiltonian. And what you do is you integrate the perturbing field around the circle and add it in. So that's a bulk Hamiltonian. So what's the condition for this defect to be translation invariant, this perturbed defect? So the ingredients are a bulk field, some defect fields, and a defect. And it turns out that in the case where this quantity is well-defined, so in particular, to be well-defined, you want no ultraviolet singularities. So your integrals all make sense. There's no regularization required. This is not a quantum field theory with infinities you have to control. We want to choose the dimensions h and these things such that this is a finite, well, it has no infinities in it. It's on a finite size system, so there's no infrared divergences. So there's no ultraviolet divergences, no infrared divergences. You can do the calculations without worrying about any of the regular stuff. And there's a simple condition. If this condition is satisfied, on the commutator of the defect with the perturbing field related to the commutator on the defect of these defect fields, if that is satisfied, then your perturbed defect is translation invariant. So what this means is, here's my defect. I have to commute it, so I'm taking the field on one side with the field on the other side, taking their difference, and it has to be equal to, I've dropped the coupling constants, the difference of these two fields on the defect in opposite orders. So there is no requirement that these have to commute on a defect. A defect is a line. You can't take 2 points past each other on a line by analytic continuation. These structure constants don't have to be symmetric. Sorry. So these are structure constants. I think of what these things, this thing comes to here, it expresses over a set of fields. These are expressed over a set of fields. These are structure constants. These are bulk to defect structure constants. These are defect structure constants. These do not have to be equal. Not a requirement. Typically, they're not. So when this was first looked at, I looked at this with Zoltan Beinok some time ago. We expressed it in terms of structure constants. in a standard way about a conformal field theory is defined by operators, dimensions, and structure constants. We expressed this commutation relation in terms of structure constants and showed it was true in the Li-Yang model.
Excuse me.
Yes.
This looks a bit like discrete holomorphicity. Is there a connection?
We should talk. I see. I don't make a connection in my head, but I see what you mean. So what happens? Here's our condition. If the field commutes with the defect without the requirement for these extra terms, that means that the topological effect is preserved by the bulk Hamiltonian. We're looking at a preserved non-invertible symmetry. That's not what we're after. We're after the case where the field sees the defect. So we actually have to have the right-hand side non-zero. And you can see this is satisfied by a relation between mu and lambda, lambda tilde. So there's a one-parameter family. We fix lambda, it determines lambda tilde. We get a one-parameter family of non-local conserved charges. You think of these perturbed defects, they commute with the Hamiltonian. That's a charge. They're defined on a defect by an integral. That means they're non-local. And there's a one-parameter family of them, labeled by lambda. We fix mu to define the bulk theory. We fix lambda, and lambda tilde is basically mu over lambda. So we have a one-parameter family. Moreover, they commute. In every case where we've looked at the commutation relations, which is not all of them, they commute. So we have a commuting set of non-local conserved charges. And I should say that there's a nice interpretation in sim-TFT for this commutation relation. I see I've got 5 minutes left, so the reason of expressing it this way, sim-TFT, or topological field theory construction of CFT, is that using standard TFT rules, so there's some standard rules for doing TFT manipulations, and a basis of your defect fields, you can express the bulk commutation this way. So you map it to a sim-TFT or TFT construction, you get this equation, which is a simple equation for the kappa and kappa tilde that appear in your basis of defect fields. These FRF matrix entries, that's a Braiding matrix entry. These are just some simple equations you can now analyze. Are these satisfied or not? They depend upon, well, the field you first thought of, phi, the defect you first thought of in the model. So I've said I'm looking only at Virasoro minimal models. So these are a particular set of very well studied conformal field theories. The model is labeled MPQ, the fields are labeled phi RS. The defects are also labeled phi RS, labeled by integers R and S. The defect does not have to be simple. I said it's topological, but it can be a superposition. So in some cases it has to be. It doesn't have to be a simple defect. So in some cases we look at superpositions. So here are 3 known families. So phi 1, 3, that's an example of the tricritical Ising model going to Ising model. It works for this type of defect D1, 2, for all MPQ with Q equal 4, and the local charges are there. This phi 1, 2, that's the Li-Yang type. Here's an example of a superposition where it works. This also works for the magnetic perturbation of the Ising model. And again, infinite set of models, infinite set of local charges. There's one rated by duality, phi 1, 5. So in all these cases, these mutually, those are known. I'm going to say this. You can also show that the perturbed defect satisfies this fusion relation for the case of phi 1,3 in Li-Yang. That's a fundamental fusion relation. It's the same as a T-system relation, which is the basis, I think, one of the bases of Bazarov, Lukyanov, Samlogikov's 1994 work, and the relation to TVA equations. So you can prove this. In CFT, Ingo did this in 2007. Other perturbations, let me just put them all up, which are not of these known integrable types related to classical integrable systems related to affine algebras, it's a much more complicated situation. And in particular, the models in which you find solutions are discrete. So it's not a case that they exist for all Q. These equations are much more constraining. So the phi 1,7 perturbation of M310 is in here. So there's a 10 here. This defect, phi 1,5, we can come up formally with non-local conserved charges for this new perturbation. In the case of phi 1,7 of M310, Q is 10, based upon the defect phi 1,5. This is another case, but 10 isn't in there. So we can formally do it. I should say formally, because in this case there are divergences. This is not a finite system. So here we are. This is the upshot. Formally, we can find a one-parameter set of non-local conserved charges, which are a possible source of integrability of the flows. They need regularization, and the fusion relation needs to be investigated. In particular, how it may or may not be broken by the regulation. This is a second application I've clearly got no time to discuss, but I wanted to leave this picture. I quite like this picture. This is about properties of a chiral perturbation in Li-Yang model, and how you can see here 5 sectors in which the number of topological defects in infrared changes discontinuously. When you look at properties in the infrared, that's a limit, R goes to infinity. Doesn't have to commute with other limits. So changing the value of lambda, changing its phase, doesn't require any continuity in the number of topological defects in the infrared. So it's quite complicated. This is a numerical technique. It's not 100% accurate, but it shows, I think you can see there's a change between this behavior here, this behavior here, to this behavior here. This is something we're looking at the moment. These are chiral perturbed defects and their properties. These are also translation invariant. And I just like this picture. I think I'm going to stop here. We ran out of time. That's a summary and outlook. These are an interesting class of objects in various contexts. They have various physical applications. They are the correct description, in some sense, of generalized Gibbs ensembles. They can provide continuous families of non-local conserved charges in models that don't look integrable at first sight. The relation to these new integrable flows needs clarification, and the asymptotic behavior related to that last slide I just flashed up, something we're trying to work out now. It looks mathematically interesting. I'm not quite clear what the physics is, but it's intriguing. Okay, thank you very much for your attention.
More questions? Yes, please.
You had this relation between mu and lambda on this flow. Is this relation something that you have to fine-tune, or it's somehow natural on the flow? It's protected by something.
So this is looking at the integrability at a fixed value of mu. We want to know, at this value of mu, is it integrable? So in that context, we don't need to fine-tune anything except the mu equals lambda tilde relation. So we have that's the condition for this conserved charge to exist. Okay? And then as we increase mu, we have to change lambda and lambda tilde because they have to satisfy the same relation. It's not the case that they flow along here. I mean, I think they do, but Anatoly's looking. Okay. But at the basic level, we just want to think, at this value of mu, is it integrable? Do we have conserved charges? So we can do. We can have conserved charges that look, we don't know what they're good for. That's one of the things. You'd thought if you had an infinite family of conserved charges, you could do something with them. If you look back to the BLZ relation, what they're actually looking at is the asymptotic properties for large lambda as an expansion over local conserved quantities. And we're struggling to find the local conserved quantities that they could expand over. So the question is still, we might have found an interesting algebraic structure, but it still may not guarantee integrability, even though it's complicated. So I think the question of whether these are integrable or not, and whether this construction can be used to prove integrability is still wide open.
You have also a question, how much of your discussion is still true if you do things on the lattice?
Well, I know that things on the lattice that are inequivalent become equivalent in the continuum, like these. You know, you can get one lattice shift in some equations, which mean that things that look like they should be true end up needing to be adjusted. So I can't say. I would expect that the broad framework remains true, but the details, I don't know. Okay.
Yeah, thank you. So perhaps I missed your explanation, but so my question is, so I understand that if you consider GG using the conserved charge, it naturally gives a translation invariant effect. But my question is, okay, forget about the massive deformation, just focus on CFT. And if I find the conserved charges of given CFT and introduce GGE, then it's translation invariant. That's kind of obvious. But the conformal invariance of this defect seems not obvious to me. Is that naturally?
No, it's not conformal invariant. It's not required. It's not. Just translation invariant.
But eventually, this defect would be renormalized into conformal invariant. Can we track how this GG is renormalized into?
I have not thought at all about renormalization group in relation to GGEs. I'm sorry, this is simply with a fixed GGE. I have not thought about that at all. Sorry.
There was one last question somewhere. Yes.
No, sorry, this is again an extremely elementary question, but in your slides about the Virasoro minimal models,
yes,
if I understand, I'm just probably missing something, but these defects are also operators acting on the Hilbert space of that minimal model, is that right?
yes.
But earlier on, when you were talking about these, when you were computing these traces on the representations of the W algebra, right, those were also interpreted as defects. But you said that you were changing the Hilbert space somehow, right? What was I misunderstood? Is there what's going on in these?
Oh well, so that's true in CFT. If I take a CFT on a cylinder,
Right.
sorry, do we have some chalk?
Yeah, over there.
Sorry. Okay, thanks. So if I think of the defect acting on a Hilbert space, it does. So I think of a Hilbert space attached to here, I map this to the plane. This circle gets mapped here. This acts on a Hilbert space. But if this is a torus, then it's equally equivalent to the defect running along, which when I map it to here,
Oh, I see.
change the Hilbert space.
I see.
So in one picture it's an operator, in the other one it's the hill of the space that changes.
See, somehow, when you've constructed the torus, somehow it runs in a different direction.
Yeah.
See? Okay, yeah, thank you, that's very clear.
Okay, so let's thank Gerard again and let's reconvene at 11:30.